4. Okay, let's talk about 4. So for 4, it gives you the substitution. What's the substitution? Negative sine theta. So they just do the substitution a little differently. So you do you can do the substitution a couple ways, but you end up the same place. So if you choose u equals d negative sine theta, so du d theta, as stated right there, is negative cosine theta. So what we've been doing is saying du is equal to negative cosine theta d theta. So what does d theta equal? Du over what? Negative cosine theta. So what does that simplify to? When you plug this in, it ends up simplifying to that. It cancels with the cosine and adds in a negative. When you plug this in right there, the cosines cancel, and what are you just left with? The negative, which pops out there, so it's just e to the, well, u is negative, so it's u. So look, you get that. The substitution is just handled a slightly different manner. It's the same thing, but you end up, it's a little different, but you end up in the exact same place. Does that make sense? Yeah. Yeah. So let's do this one out. Actually, you know what we'll do? Let's do it. What did it say we should use for u equals x to the what? 1/3. So let's rewrite this and see why that's the case. If you rewrite this, this is just 0 to 8 of e to the what? X to the 1/3 over x to the what? It's x squared to the 1/3, right? So can you rewrite that a little bit more? That's 0 to 8 of what? Ex to the 1/3 over x to the 2/3 dx. So they said for this one, what u value should we use? X to the 1/3. So du dx is equal to what? 1/3 x to the negative 2/3, right? You go down 1. So then what do you get? You get du is equal to what? 1/3 x to the negative 2/3 dx. So dx is equal to what? Du over 1/3 x to the negative 2/3. What should we do before we simplify that? Oh, I just said it out loud. Before we substitute it, we should do what? Simplify it. Dividing by 1/3 is the same as multiplying by what? So you have that equals, let's do it piece by piece, 3 du over x to the negative 2/3. Where can we bring that x to the negative 2/3 and make it positive? Yeah, it's 3x to the 2/3 du. So that is dx. So when we make this substitution now, what do we end up with? We end up with the integral from what to what? Careful, not yet. E to the u over x to the 2/3 times, what was it? 3x to the 2/3 du. What cancels? What's the nice? This, see?
Wait, why did the x go up to the x? Like go up to the black?
Yep.
Why is it in the exponent? Is it always in the exponent?
What's always in the exponent? I'm sorry, what are you saying? Cancels. What's x to the 2/3? That's nice. And what can we factor out to the front? Now, are we in x's or u land right now? U. So we have to use u values up here. What's the relationship between x and u? What does u equal? U is equal to what? U is equal to x to the 1/3. So what's u of 0? That's 0 to the 1/3, which is what? And what's u of 8? What's 8 to the 1/3? What is it? Exactly. So this is 2 and this is 0. You do that so you don't have to substitute at the end. So what's the integral of e to the u? E to the u plus c. You don't need that c because you're integrating it. It's definite. It's going from 0 to 2. So what is that? 3e squared minus 3e to the 0. So that's 3e squared, not to the 0. 3e squared minus what? Minus 3. You'll either see that as the answer, or what's the thing that they like to do sometimes? Factor out 3, so it's e squared minus what? And sometimes you might even see it like this, 3e minus 1 times e plus 1. I am totally okay with the squared one. The boxed one, this. I'm totally okay with that. Not have to simplify, not have to resubstitute the whole equation. It's much easier, I think, to substitute numbers than it is whole equations. Am I looking for something that's perfectly exact? No, it's really hard to draw some of these if they're perfectly exact. So you have your parabola like this, and it's at x equals, so it's going to be what? Like starts here at 0, 4. It kind of goes up like this and up like that. And you're going from x equals negative 2 to x equals 4. Nice. So if you wanted to find that area, what would you need to do to find the area of that region? What's the integral you would need? The integral from what to what? Negative 2 to 4 of x squared plus 4 dx. Now, is that something you could do on your calculator or by hand?
Yeah.
Absolutely. We're not going to do that right now, just in the interest of time, but are you confident that you could figure that out?
Yeah.
Absolutely, you could do it. Fantastic. What are you doing when you do that? You are taking lots and lots of rectangles, and you're adding up how many of these rectangles? How many rectangles are you adding up when you find that area?
A lot.
Yeah, what's another word for a lot?
Infinite?
Yeah, an infinite number of them. So you have these rectangles, and as you make an infinite number of them, so like here's one of the rectangles, here's another. If you don't do an infinite number, if you do anything less than an infinite number, you don't have an accurate, well, it's accurate, it's just an overestimate, right? Yay. Okay, so you can do that by calculus, calculator or by hand. So draw me, so if you found this one, you know what? We can plug it into our calculators and we can find the answer. Do that right now. Use your calculator and find me that. Use your calculator and find me the answer. Oh, wait, I'm sorry. Excuse me. Excuse me. Put your calculator away. Excuse me. Sorry. Draw me the picture first before you use your calculator. Do that on this. Write down what you think the integral is for that blue area. What is the integral? What integral do you need to solve for that blue area?
-2.
Yep. What's the upper number, Maggie? Oh, okay. It's okay. It's 4. And then anybody want to guess what goes on the inside? Sarah, what is it?
X squared plus 2.
X squared. How'd you get that? X squared.
Plus 2.
But how did you get that?
Because I took 4.
Yep.
And then subtracted the 2.
Yeah, that's right. It's the upper minus the lower. We've done this kind of thing before. It's the upper minus the lower because where are the rectangles now? Here they are. The dx is right here. That's the dx is the width. And what's this height? If you wanted to know what that height was, that's x squared plus 4 minus what?
2.
Yeah, so it's x squared plus 4 minus 2, so it's x squared plus 2. So could you solve this?
Yeah.
Yeah, it's a polynomial. Are you pretty comfortable doing this by hand? X squared plus 2 dx. So if you're doing that by hand, it's going to be x cubed over 3 plus 2x from negative 2 to 4. What do you think the most common way people mess this up is? What do they forget, skip, or otherwise ignore? It's one little tiny horizontal line. The minus part, actually. So because you have to subtract this, right? So what is this going to be? It's going to be 64 over 3 plus 2 times 4 minus negative 2 cubed over 3 plus 2 times negative 2. Are there lots of places to get the negative wrong? Yeah, so what do you have? 64 over 3 plus 8 plus 8 over 3 plus 4, right? They all turn positive. Do you agree with that they all turn positive? So there are a lot of ways to get, oh yeah, 72 over 3 plus 12. So that's 72 over 3 plus 36 over 3. So what is it? 108 over 3? And that's actually what? 36. 36. Yeah. Good job. So you can do that by hand. The most common mistake people make has to do with negative signs. Absolutely. The most common mistake. It's kind of comical how often that happens. So you need to be careful about that. When you went about drawing this, they're just vertical and horizontal lines, correct? So what do you end up with here? You have y equals 5. So maybe something like this. Yay, y equals 5. And then maybe what, x equals negative 2? X equals negative 2. And let's go with red here. Was it x equals 4? X equals 4. So the other bound is going to be the axis, the x-axis. So this is the region right here. What type of shape is this?
Rectangle.
It's a rectangle. Exactly, it's a rectangle. So guess what we're going to do here? So we're bounding it by the x-axis because we're about to, so it's about the x-axis, meaning we're going to rotate it around the x-axis. So we're going to go from 2 dimensions into 3. So imagine so the radius would be actually, so let's label some points. Here's A, here's B, and I'll call this point C. Where's the radius of the cylinder? So that would be the radius, right? And what would be the height of the cylinder? A to C. Exactly, exactly. So if you spun this, what are we looking at? We're looking at something that ends up looking like this. It goes out a little bit at an angle, and it goes out a lot at an angle, a lot like this. If you keep on spinning it, what do you end up with? A cylinder. Nice. Does everybody see the cylinder I'm trying to draw there?
Yeah.
Three-dimensionality is a little challenging. The one hint I can give you for drawing three-dimensionality, limit the number of lines as much as you can. Limit the number of lines as much as you can. And that's nice. I'm not trying to pause it. I want to pause there. You know what the radius of the cylinder is. It's from here to here. It's what? 5. What's the height of the cylinder? You got it. It's right there. 6. Do you remember what the volume formula is for a cylinder? That's it's pi r cubed is there. It's not quite. Pi r squared is the base, but then you have to multiply it by the height. So it's going to be volume is going to be in this case pi times 5 squared times the 6. So it's going to be pi 25 times 6, which is what? 150 pi. Whatever the units are, it'd be 150 pi cubic units. So what's nice about this, all of our boundaries, our top boundary and our bottom boundary when we rotate is always going to be a line. We're always going to rotate over a line. We're always going to go from an x value to an x value. So this is always a line, this is always a line, and this is always a line. But is this always going to be a line? No. Has anybody used the lathe before, or like spun a pot for clay? Everything is spinning. Like, see a piece of wood and it spins, you can like make a baseball bat. So like the function goes like this, and then it spins and it creates the baseball bat. With a pot, it's spinning a lump of clay. So if you made slices, what would you see? You'd see lots of circles. If I were to slice this, what do I see? Lots of what? In this case, it's all circles that are all exactly the same. If you stack circles that are all exactly the same on top of each other, you get a cylinder. But if you change the size of the circles, what can you get? A baseball bat. Or you could get, for example, anything that's a rotational solid. So what I mean by that is this. Let's say I had a triangle like this. Let's say I spun that triangle like this. What would I get? Here's a rotational solid. So what would I would get a cone for this one. Is this a rotational solid? Why is this a rotational solid? That's true, but as I'm spinning it, does the outline change? No. I'm spinning this, but the outline doesn't change, right? If I were to cut this, or let's say it was like this, if I were to cut it like this, what would you see? Circles, 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 but they would all be what? They'd all be different, well not all be, some of them are the same, right? But they would all be circles. If you slice something with parallel slices and all you get is circles, it's a rotational solid. So what we're going to learn is how to find the volume of those rotational solids. This one was really nice because it created a shape we already know. What shape did it create? A cylinder. So let's look at one, if we were going to use calculus like we've used before, one rectangle. Remember how we add all integration is adding up rectangles? What did we call the width of each of those rectangles? What was the width called? dx was the width. What's the height of each of those rectangles? In this case, all those rectangles have the same height. What is the height? It's the r value. What's the r value? What is it? Actually, what's the number? It's 5. Do you agree that the height of each of those rectangles is 5? It is the radius, but it's the height of each of those rectangles. If you spin this rectangle, what do you get? If you spin this rectangle, what do you get? You get a cylinder. It's a very, very skinny cylinder, right? But if you spin this, you get a cylinder, right? Looks like a little coin. Does everybody get that? What's the volume of that? Remember, we already know what the volume is for one cylinder. It's pi times r squared times h. But what did we say h was? D what? Right there, it's what? In this case, for this little tiny one, it's dx. So it's pi r squared dx. But what did we say the radius was for this entire thing? 5. Is everybody with me so far? If you want to add together an infinite number of things, what have we used to add together an infinite number of things? The what symbol? The integral symbol. Where is the disk that's farthest to the left? What disk is farthest to the left at x equals? So it goes from -2 to what? 4 of pi times 5 squared dx. Let's see what happens when we do this. What can we factor out to the front of that integral? 25 pi. Integral from -2 to 4 of what? dx. What's the integral of just dx? What is the integral of dx? Yes, it's just x. So it's 25 pi x from what to what? -2 to what? 4. So what is that? 25 pi times what? 4 minus -2. What's 4 minus -2? 25 pi times 6 is? What is it? 150 pi. Is that the exact same thing we got before? So this right here is how you can get the same answer. The only reason, what's the only reason we could use this method right here? Because it is a cylinder. But this edge right here, do you see this edge? If I took this piece of wood, this dowel, and I spun it on a lathe, could I do anything I want to this function right here? I can make it curve down and go up, right? I can go up and down, up and down, up and down. It wouldn't necessarily be a cylinder. The point is this is a cylinder, so we have an easy way to do it and a slightly harder way, but here's the thing. Are we going to have a formula? Like, for example, do we have a formula for the volume of this nested doll? No, but might we have a formula for the function on the edge? Yeah, like that looks like a polynomial, right? Like it'd be like a fifth degree polynomial. Do we know how to integrate polynomials? We know how to integrate polynomials. So what we can do now is use something other than straight lines. So this is what I'd like you to do. Graph this for me. Graph, not the rotation. 1. What's 2 times 1? 2. So this point right there, what is that? 0, comma 2. And it goes up in an exponential function. Do I care about how exact you are in the curve? No, but you know it goes up quickly. So that's what it looks like. What are we going to do with that shape right there? You're going to get the down angle one. So that would look like this. So there's the bottom half of it, right? See the bottom half right there? What are you actually going to see if you like took a point here? If you spun that point, it would be like this. It would go like this. It would go like this. And then you would see, what would you see at the front here? So what does this shape look like in 3 dimensions? Turn your head sideways. What does it kind of look like? It kind of goes in though, right? Someone said volcano in the last class.
Yeah.
Kind of looks like a volcano. Does everybody see it right there?
Yeah.
When you do rotational solids like this, draw as few lines as possible. These continue around back, but if I draw them, it gets real busy, right? You see what I mean? But if you were to look at this straight on, you would see a circle. Let's say you took that one slice off, what would you still see? A slightly bigger circle, right? What's going on here is we're going to rotate a whole bunch of rectangles. What's the width of each of these rectangles? We already know what that is. What's the width? D what?
Yeah.
The width is dx. So we have dx, r squared, and pi. That's the area, that's the volume of one of these little rectangles spun around and turned into a cylinder, right? So we need to know r in terms of x. What's the radius? Can someone tell me what the radius is? It's right there. The radius was 5 before. Why was the radius 5 before? It was y equals 5 was the function, right? What's the radius now? What? 3 to the x. Exactly. R is 2 times 3 to the x. The radius changes depending on what x is. Before it was constant. It's a lot easier when it's constant. So what do we have for our integral? What's the lowest x value? What's the lowest x value? 1. What's the highest? 4. And then we have pi times 2, 3 to the x squared dx. Is this an integral we can do by hand? What do you think? What do you think? It absolutely is one we can do by hand. What do you need to do before you integrate it? What should you do first before you integrate? Simplify this as far as you can go. Do that now. You can sit to that go. Oh, shouldn't do that. It's going to be 1 to 4. We can pull out the pi, but it's 2 what? 2 what? What do you have to do with the exponent right here? 2 to the what? And then times 3 to the what? 2x dx. What can you still factor out? So you have 4 pi, 1 to 4 of what? 3 to the 2x dx. And this is something you absolutely can integrate right here. Go up to the board, everybody. So walk me through this. So when you do this, you have to remember the chain rule is in effect here. So you could use W substitution. If you wanted to use W substitution, you let W equal 2x. I think that makes it I don't think you need it. I think you can integrate this without W substitution. That's my opinion anyway. So you'd end up with 4 pi times 3 to the 2x over 2 ln 3 from 1 to 4. And then it's just a matter of simplifying it properly. You have 4 pi 3 to the 8 minus 3 squared over 2 ln 3. That's what you end up with, right? Yeah. And then I just wanted you to practice some simplification here. So if you simplify that, you can end up factoring out 4 pi over 2, and then you can factor out a 3 squared from the top, right? So keep track of what you're canceling, that that 2 and that 4. So you end up with, you could write it as, what is it, 9? No, 18 pi times 3 to the 6 minus 1 all over ln3. That's a great clean answer right there. I love that. I love that. Love it.